All right, are we back? My signal just disappeared. Excuse me. All right. All right. Welcome back. All right, guys. So where was I? Okay, I was talking about iron two oxide. This reaction in the presence of aluminum gives us iron and aluminum oxide, which is an example. Anybody remember what type of reaction this reaction is an example of? One of 6 reactions types. No, don't remember what type. What we got here? Yes, single replacement. You got it, both of you. Single replacement. Aluminum is a lot more reactive than iron. Aluminum is not in ionic form. Therefore, the metals exchange and you regenerate iron. Okay. All right. So we had the first question was, let's go back to review here. We went back too far. We want to calculate the mass of iron 2 oxide needed to react completely with 5.5 grams of aluminum. Okay, so we will need to know how much other reactant iron 2 oxide is necessary. Well, the first step when you're in grams, you need to get to moles. Remember, I can't get to apples to oranges unless I get through a common factor, which is moles. So since aluminum is just and the element, we simply need its atomic weight. Okay, its atomic weight then gives us moles of aluminum. From there, we use the stoichiometric relationship between the two reactants to get us into moles of iron 2 oxide. Think about this for a second now. All right, first one, notice that the grams of aluminum cancel out, leaving us with moles of aluminum if we were to stop there. But no, we're trying to get to moles or grams of iron 2 oxide. And so our middle conversion factor now converts us from moles of aluminum to moles of iron 2 oxide. Okay, keeping track of my units. So now at this point, if I just stop the math, I got moles of iron 2 oxide, but I need to get to grams. So now I need the molar mass of iron 2 oxide. And if you add up the atomic weight of iron and oxygen, it should come up to 71.85 grams per mole. And then along the line, keeping track of your units. That's what we're looking for unit wise. We're looking for grams of iron 2 oxide. And so here, if you recall, I stated that you're going to use at the minimum 3 conversion factors. And here we are. The first one got us to moles of aluminum. The second one, here we got us to moles of aluminum. Okay. The second factor got us to moles of iron 3 oxide. And the third one got us to grams of iron 3 oxide. Okay. Doing the math, that means that for this reaction to proceed completely, we would need 5.5 grams, 22.2 grams of iron 2 oxide and 5.5 five 5 grams of aluminum. Okay. Now we didn't calculate any of the products. All we did was just, okay, I started with 5.5 grams of aluminum. How much aluminum, iron two oxide do I need? That's all we did. Okay. Now, now we start off with 10.2 grams of aluminum, and I believe we were looking for the amount of aluminum oxide here. Okay. So first step, convert to moles of aluminum. Okay. Second step, get us to aluminum oxide from the balanced chemical equation stoichiometry, which is a 1:2 ratio. And then finally, get the molar mass of aluminum oxide. 2 aluminum, 3 oxygens has a total molar mass of 101.96 grams per mole. Check your units as you set this up. Okay. You can see here that grams of aluminum cancel, that's proper. Moles of aluminum cancel out, moles of aluminum oxide cancel out, leaving us with grams of aluminum oxide, which is what the question asks. Okay. This, ladies and gentlemen, is what it means to show your work if you have to show your work, because you might have a different answer, you know, and maybe you come up with, say, 11.11, an example on top. Obviously, that's not the correct answer, but if you got everything else set up properly, you will get credit for everything you set up. Okay, so this setup in number one, it could be worth, let's say, 4 points, for example, 4 points for the setup, and maybe 1 point for the answer. So if you just present the right answer, okay, that's fine, it's good, you earn 1 point. And on the same token, if you present a wrong answer, but you set it up properly and everything looks good, you get the full 4 points. You won't get the full 5. Only if you got the setup properly and the answer is correct. I do that because, you know, I don't see why you should be penalized for giving the wrong answer if you set it up properly. You should not be penalized for setting it up properly, but definitely penalized for not paying attention to your calculator and pushing the wrong numbers. Okay. All right. So that tells us here that if we start off with a 10.25 grams of aluminum, okay, I will make 19.37 grams of aluminum oxide. And this is true if this ratio and this type of calculation is true if I'm trying to make 19 tons of this material. All right, so the flow chart overall, it helps you. My suggestion is this flow chart, you got it, you understand how it works. You should not have a problem if you set up your problems like I just demonstrated here in the ratios and check your units, and you follow through your thinking process using this flow chart. I guarantee you're not going to have a problem with looking at these problems that look very complicated by the way they're stated, but really are not. They just look complicated, but you just break it down. Anything complicated, the best way to attack it is to break it into pieces. You know, small pieces, and you're able to get to the whole thing. But here's the thing with this flow chart. What we've been doing is we've been given grams of something, and we're looking for grams of something else. We cannot go directly like so, okay? Cannot do that. We have to travel through moles, okay? And so if I'm given grams, obviously the first thing I need is the molar mass or atomic weight if it's an element. So I need the molar mass because dividing by the molar mass gives me the moles that I'm given. The mole ratio comes from the balanced chemical equation, which pertains to the two entities that I'm trying to calculate. Okay, you're only going to be calculating uh, two entities. In other words, you may have two reactants and two products, but during these calculations, you'll be maybe between the two reactants or between one of the reactants and one of the products, and that's it. Everybody else in the equation we don't have to worry about. Okay, so the the mole ratio, which comes from the stoichiometry of this reaction after it's balanced, then leads us to the moles that we're trying to find. Okay. And then from that, knowing the molar mass, which you should be able to calculate because hopefully you need the formula, which brings us back to writing formulas is what we've been doing. Remember, we started with the elements. We started with writing ionic compounds. We started with these elements that lost or gain electrons, and then we started putting them together. We started naming them, giving them names. And now we put those compounds together to form reactions. All right. Then we learned to balance them. All right. And so here we are. We're trying to put everything together that we talked about. Okay. And this chapter does put everything together. So from the molar mass, then we can calculate the grams that we're looking for. Now, the things in yellow, only at STP. Remember when we talked about S standard temperature and pressure, 0 degrees Celsius and 1 atmosphere? We had that relationship that 1 mole gas occupied a volume of 22.4 liters. So from this point, you can incorporate those type of calculations with those reactions that don't deal with STP conditions. Okay. But regardless of that, I can go from grams given all the way over to the bottom left corner to figure out the volume if I'm at STP only. Okay. And then here I need the molar mass, gives me the moles given, then being STP, 22.4 liters per mole, I have the gas. Okay. Or I can go from grams given, shoot across diagonally, and get my way all the way down to find the amount of the volume of a gas in this reaction. I could have a reaction that at STP produces, say, hydrogen gas. I can calculate that. Okay. Now, I'm drawing the arrow one direction, but remember, that arrow can go two directions. It can go that way and it can go this way. I could be starting at the bottom right corner and I go to the top left corner. Now, or I can cut a corner. I can go from bottom right corner to bottom left corner. Okay. And the other directions, I can go bottom right corner to top right corner in whatever combination else that you need. Okay. But before I can do all that, I can't go directly. I go using the moles. Okay. Moles is what gets me the mole ratio, and moles is what gets me from point A to point B. Okay. Anybody have any questions about this particular flow chart? So it's a very important flow chart. I think if you study it well, see how it goes from point A to point B, you shouldn't have any problems. Okay. All right. balance, see, because here we go. We're given a sentence, okay? And now we got to convert this sentence into an equation. It says here, write and balance the reaction of hydrochloric acid aqueous and solid cobalt. Okay. Well, let's do that. All right. So we have HCl aqueous reacting with solid cobalt. Oh, my resolution of my pen is not the best. That looks more like carbon monoxide. Cobalt. Okay. Now, question is, what is the product here? Okay. Does this what type of reaction does this look like? Who wants to give it a shot? Or some other information. And since cobalt is not one of the sweet 16 metals, has a variable oxidation number, they need to tell you here that cobalt will be a +2 ion in this reaction. Okay. But what type of reaction? How would I know what the products are though? Okay. I'm just been given this reaction and I'm like, Anybody want to give it a shot? What, let me give you a hint. Right here, you would need the activity series. Okay. Notice cobalt. Cobalt is a lot more reactive. Remember I stated that these activity series are relative to H, hydrogen. And the ionic form of hydrogen is H plus, the proton, okay? Or it could be water. But here we're given HCl. So hydrogen is in the form of H plus. So the activity series says that cobalt is a lot more reactive than hydrogen. Okay, so let's write it again. So we have hydrogen, HCl, plus cobalt. And we know from the activity series that cobalt is I keep losing my connection here. Oh boy. Yeah, you're right. What time is it? I don't know. I use Cox, so I don't know if it's Cox that gave me trouble or what the deal is, but it's the most trouble I had in months. All right, so what time is it? 2:15. Tell you what, why don't we stop it here? I don't know what the recording is going to do. I think I'm gonna have 2 recordings. So as let's stop it here. We'll continue. So this would be slide number 8.